And so we're going to talk a little bit about solar, how it works, and things that you can do if you're thinking about a solar array, whether it's for a school or a business or a home. And so that's really what we're going to talk about. I work a lot with a company called Solar Plexus out of Missoula. They install solar panels, and so a lot of the images that you'll see have actually come from Solar Plexus here in Missoula, Montana. Okay, so first of all, let's go ahead and get started. This is interactive. I'm going to be talking to you a lot, asking lots of questions. I even have a math problem for you. How about that? What? Math? How does that work? Okay. All right, so this great giant orb behind me, what is this?
The sun.
It's the sun. Does anybody want to know how much energy the sun is putting out at any given moment?
How much energy is it putting out? You guys hear? Trying to entertain us.
50%.
How about that? So this is how many joules or watts per second the sun is giving, which is 3.8 octillion, or 3.8 times 10 to the 26th. So that is a lot of energy. And so we're going to talk about how we can use this energy. Now, all right, to define energy, this fellow behind me, who is Einstein, came up with which equation?
E equals mc squared.
Yeah.
Perfect.
That.
What does E equals mc squared mean? Or what is the E, the m, and the c squared?
Energy equals mass.
Divided by mass. I don't know.
I know it's energy.
Yep. So exactly, it's talking about energy. So E, which is energy, equals mass times the speed of light squared. So the idea is that we can measure how much energy something is giving off or something contains based on the mass and how fast it's traveling. So when we're looking at the sun, that would be an equation that we could use to help us get an idea for how much energy the sun is producing. And so that equation has helped us a lot with those energy producing questions. How much energy does this create, or does this use? So this is a little basic. So our Earth right now is using about 1/10,000th of the amount of solar energy that is available at any given moment. So we're using a very, very, very small percentage of this. And so I had a good question. My husband the other day, he said, well, I don't know, I'm going to argue with you. Does that include the energy that the sun is giving to the plants to grow? Because that's certainly solar energy. And I said, I'm not sure about that. That's a good question. I'm pretty sure that this number refers to active solar. And we're going to talk a little bit about the difference between active and passive solar. Does anybody have a guess right now what the difference between active and passive solar is?
Well, I think it would be the use of solar for energy, that powers electricity and stuff.
Yes.
And the passive would be all the plants and everything that it powers otherwise.
Absolutely. So I'm going to give you a few examples. Let's see here. Solar photovoltaic, so solar panels, passive or active?
Active.
Active, very good. Hanging your clothes to dry in the sun.
Passive.
Perfect, that's passive. Let's see, how about solar thermal? This one's
That might
tricky.
be between, I'm not sure.
Exactly. This is almost like a trick question because it really depends on what type of solar thermal. So solar thermal is using the sun to heat up hot water. Now you can do it passively, where you just have the sun heat up hot water, or you can add an electrical component to it where there's a pump or something else that's helping move that, that's helping increase that efficiency of that system. So you can be active or passive. So we'll talk a little bit more about that later. So, but anyhow, the idea is that we really are not using that much of the sun's energy at any given point. Our world energy consumption is approximately 474 times 10 to the 18th. Okay, so that's a lot of energy that the world is using. These are just some little facts. Approximately 2% of the sun's energy is reaching the Earth. So, and of that equates to about 7.6 times 10 to the 24th watts. So that's about how much energy at any given point the Earth is receiving from the sun. So if we look at this number and we look at this number, which one is larger?
Low consumption? Or
this one. So we got 7.6 times 10 to the 24th. So we have a lot more zeros on this one than we do on this one. And when we start talking about numbers that have 24 zeros after them, we're talking about really, really large numbers. So we know that we have a lot of energy that is left to use. So just to give you an idea, if we were to be using all of this energy that we had, we could cook about 2 sextillion, 615 quintillion, 472 quadrillion, 127 trillion, 519 billion. Oh goodness, I'm off. But anyhow, a ton of hamburgers per hour. That's how many hamburgers we could cook if we were using all of this sun's energy. Just to say, this is a very theoretical idea, but it gives you an idea of how much energy is actually available from the sun. Okay, so I said that we were going to be talking about a couple different types, and I just want to show you some of those types of solar energy. So first, there's photovoltaic. When I say photovoltaic, I'm going to be referring to solar panels. That is what we call solar panels, is photovoltaic. Today we're talking mainly about solar panels. So when I say solar or a solar array, I'm referring to solar panels. Then we have a solar thermal. That is hot water. And like I said, it can be either active or passive depending on the system. And what that does is it heats up hot water. It uses the sun's energy to heat hot water. Now, something that's kind of interesting is that there's a new building code in Hawaii, or it's relatively new. It's probably 5 or 6 years old at this point. And if you build or add on to a structure in Hawaii, you're mandated by law, by the building code, to have solar thermal on your roof. And there's a lot of different ways you can do that. But what it does ultimately is, you can imagine Hawaii is this island. They have to import a lot of what? Can you guess?
Water.
Water. They have to import a lot of everything. It's a pretty small island. They have to import a lot of everything, including energy, including coal, including gas, whatever they are burning, whatever they are using to create that energy. But what is something that Hawaii has a ridiculous amount of?
Precipitation.
Water.
They have water. They have tons of water. What else?
Wind.
Say it again louder. Trees.
They have trees. They do have some trees. I think I heard it. They have solar energy. If they have so much solar energy, the sun shines almost every single day there. They have tons of solar energy, and they are saying, listen, we can take care of some of our energy needs by using the sun. If you were to go to Hawaii, it is around 5 times, the electricity is about 5 times more expensive in Hawaii than it is in Montana. Sometimes it's even more, just depending on the cost of coal, the cost of natural gas, things along that. So imagine taking your energy bill and raising it 5 times. It'd be humongous. So that's definitely something that they're working on. By doing something like adding solar thermal to the roofs, that greatly reduces the amount of energy you're using. So here's another example of passive solar, and this is a great picture of a passive solar house. Passive solar house means that you are using the sun's energy to help warm your house, or you're using shading to cool your house, but what you're doing is you're not using as much energy that comes from coal or any active source, natural gas, things of that matter. And so what we can see here is we'll see a few different things. You'll see windows that are predominantly on the south and or west side of the house that are going to be using that for both natural lighting and for heat. So this is something that's pretty interesting. Pretty interesting also in Montana when you think about this. It's building a house in Montana that's going to be a passive solar house. It's going to be a lot different than, say, building a house in Florida. You certainly have different things to think about. In Montana, we want to gain a lot of that heat from the sunshine because we have a lot of times where it's very, very cold in Montana. In Florida, they sort of have the opposite problem. They need to get the light from the sunshine to light the interior of their house, but they certainly don't want the extra heat because cooling is a very, very expensive thing for people in warm places that use a lot of air conditioning. So that's a whole other topic for a whole other day, is the passive using solar as a passive topic. But what I said today, we're going to talk a little bit about solar panels, talk about an array. So the first thing I want to do is how it works. How many of you have ever been up close and personal with a solar panel? Anybody? Oh, good. A few of you have seen them pretty close. So I have a little diagram explaining how it works, and I'll get into it a little bit better. But we'll talk this is the very brief part. So Sun hits the solar panel. Solar panel makes electricity, goes down to what's called an inverter box, goes into your electrical panel, and then it's able to power your appliances or your lights, okay? Pretty basic. We'll get a little bit more into it in just a minute, but that's the general part. We need to understand a few things before we do that. All right, watt, what is it? What is a watt? Oh, good, I'm glad somebody traveled.
It's a way to measure something.
Yeah.
Yes, that's exactly. It's a way to measure something. And what are we measuring?
Energy.
Yes, we're measuring energy. Exactly. So we have to have a way to measure energy, especially if you're the power company and you want to charge somebody for the amount of energy that they're using. You've got to understand how much they're using, and so we have to know what to do, and that's called a watt. So these old-fashioned light bulbs that I don't know, they maybe were in existence when you were still toddlers. I certainly remember these very well. An old-fashioned light bulb, not the kind that are energy efficient that we use these nowadays. This is a standard 100 watt light bulb. That means that in an hour you are consuming 100 watts using this light bulb, and so that would be 1 unit. Now, an energy company, that number would get very, very high if you were measuring just watts. So we have kilowatts, which are 1,000 watts. And this is what the energy company is going to be measuring when they're measuring how much energy you are using, electrical energy. And so we can imagine that if we ran that one light bulb for 10 hours, you would have used 1 kilowatt of energy. Okay, so of electricity. So that is something to remember. Or let's say there were 10 light bulbs that were left on in your house for an hour. That also equates to 1 kilowatt of energy. So you can see it starts to add up pretty quickly. And it's one of those things where you've always heard your mom and dad say, turn off the light, go back upstairs. What is this? You think this electricity is for free? It adds up fast. And when you start thinking about it, you think about, well, 1 light left on, that's not that much energy. But it's accumulative, and that's one of the things that we'll be looking at. And it's one of the things that we need to understand when we're talking about solar, because we need to understand how much energy we use to be able to put the right amount of panels or solar array, build a solar array that'll cover those energy needs. Okay, so that's the first thing. So then the next thing we have to know a little bit about is AC/DC. I'll spare you guys. Obviously, this is a song from my generation. AC/DC, what is it besides a rockin' band?
Alternating current and direct current.
Alternating current and direct current. What does that mean?
I have no clue. I just remember from last year.
It's the
different
ways
that
there are
the
set through 2 different sets of electricity.
Okay, so say that again. So it's 2. We got 2 different sets of electricity. What's happening with the alternating current and a direct current?
I'm trying to remember. Alternating current is like the positive, I think, and the direct current is the negative.
Okay, so one of the things here, this is one of the ways that I help kind of differentiate and think about the alternating currents and the direct currents. Okay. So one of them is, like it says, it's alternating current. So it's a reversing of those currents. And what they've discovered is that an alternating current can travel over a greater distance without losing as much energy. So if you take anything and travel over a great distance, some of the energy is going to be lost. So when we're talking about power lines, what you start with, what you make at the power plant, is not what comes out at the other end. There's going to be some energy loss along the way. That's delivered to us in an alternating current, and that's what most of our appliances in our house are able to take. Is an alternating current. Now, if you have a power source that is right at the power, that is right there, you don't have to have an alternating current because you don't have to travel very far. And it can be a direct current. A direct current is exactly what it sounds like. It's a direct current of electricity, of energy flowing from one place to the next. Solar panels, they produce a direct current. And so what happens is a lot of times you need to have an inverter. If you're going to be using your solar panels on your house and you want to be able to use your appliances, you're going to be needing to have an inverter, which is going to invert that current into an alternating current, which then your appliances can receive. However, this is when we get into talking about a little bit of what's called grid tied electricity and using our solar panels for being grid tied. So that's one way to do it. Another way is to have all of your energy that goes into a battery that you store, or like a generator. That can take a direct current. When you do that, then you run things off your generator. You don't need to have the inverter as part of the system. So the most important thing to remember is that traditional power lines are going to come into our house using an alternating current. Solar panels are going to produce a direct current. And so when we're talking about solar energy, a lot of times what we have to talk about and consider is the inverter box that you put on that's going to invert that electricity into an alternating current so that we can use it. Okay, so we've talked a little bit about that. I want to show you a solar panel now. So I've got this guy right here. We're going to take a close look at him, up close and personal with my solar panel. This is a regular solar panel, one that you would see in an array. I believe that this is an 80-watt solar panel, and I actually have I'm going to zoom out on it just a little bit more so you can see kind of what it looks like from a larger standpoint. Pretty basic. So we talked about the energy that comes in. It hits the solar panel, then it creates electricity. Anybody know how it works? How that does that?
I don't remember. Something about sand. That's all I can say.
Yeah. Does anybody know what a solar panel is made out of?
Not exactly.
Well, it's black.
It's black. Yep. And here's a question. What does the color black do with the sun with solar radiation?
It attracts.
It attracts heat.
It absorbs it. Okay, so that's one great observation. Okay, so here we are. I'll kind of come in here. So we have our solar panel. It's made out of silicone. Okay, so really thin pieces of silicone that have been sliced and put together, kind of sandwiched together. Now, one of the things that you do when you're building a solar panel is you have to dope the silicone. It's called doping. And what they do is they introduce something else that makes the silicone unstable, because silicon is really stable. It's a very stable element, very stable. We want it to not be stable. The reason we want it to not be stable is we think about those little atoms. So, okay, who wants to tell me what's the makeup of an atom look like? What do you have in the center of it?
Nucleus.
Nucleus with photons and with protons and neutrons. Exactly. What's orbiting around the nucleus and the protons and the neutrons? Electrons. Exactly. Okay. Now here's another little question for you. Electrons. Do they like to be buddies, paired up, or do they like to be by themselves?
Paired up.
They like to be paired up. Exactly. Now, what happens? Sun hits the solar panel right here. Okay. We've doped it. We've doped these silicon squares. So that means that they're kind of unstable. That they're sitting there, but they're a little bit unstable. What happens is the sun, which are photons, not to be confused with protons. Now I'm getting them confused. Photons hit the solar panel. What happens is when the photons hit the solar panel, they jar loose those electrons because it's not a stable platform that they are hitting. They jar them loose. Suddenly, the electrons, they're buzzing around, they're spinning around. They're going to do what? They're going to try to find what?
A pair.
They're going to try to find a pair, exactly. So here's the thing. They're trying to find a pair, but the sun keeps shining on them. And if the sun keeps shining on them, the photons keep hitting them, are they going to ever be stable? No. And what happens when electrons are grooving around?
They move really fast.
Yeah, and what's produced?
Energy.
Electricity, exactly. So by knocking those free, what happens is we get an electrical current, and that's the basis of an electrical current right there, is those electrons moving around. So we get those electrons that are moving around, and you can see that we have these little lines in here. In fact, there's tons of little teeny tiny, I'm going to see if I can get this closer so you can see it a little bit better. It's really hard to see. I'm sorry, I don't have a better view. But if you were to look in these, like inside each of these boxes, there are little silver lines that are running vertically. Okay, what happens is electrons hit the metal basically right here. These are conductors. They go to the larger ones, and then these are going to send them out to the edge, which is where the electricity comes out of, and we're able to gather the electricity from the solar panel. So that's sort of the basic workings of the solar panel, using the electrons, how they use how they dope the panels to make them create the electricity. Photons hit it, knock them loose, and just suddenly we have the electricity. Okay, it's relatively simple. So when we think about it, we got to think about, now we know how that happens, we got to think about what kinds of things to take into consideration. So we decided, okay, we want to have solar panels on our roof, we want to use some solar panels on our school, what things to take into account. So one of them would be weather. Okay, with weather and with seasonal changes, you get a difference. So one of the things, temperature, and we're going to talk about this in just a second. If we have temperature definitely plays a role in a solar panel efficiency. Solar panels are rated at kind of a medium level. So you say, if you look at a solar panel, it says, okay, this is an 80-watt solar panel. Well, that's assuming that 80-watt solar panel is operating, that the average temperature is around 25 degrees Celsius, okay? So when it drops from that, or when it warms from that, what's going to ultimately happen is you're going to either have a more efficient solar panel or a less efficient solar panel. And we're going to do a little math problem here in a minute to show how that works. Another thing, of course, cloud coverage. When we have cloud coverage, is it going to be as efficient? No, it's not going to be as efficient. Absolutely. So seasonal. Another thing to think about, if you think about the sun in the sky during the different seasons, does it stay in the same spot?
No.
No, it doesn't. It moves all around. So these are all things that we want to take into account when we're thinking about where we want to place our solar panels and how much we need. Okay, so this is a pretty fun gadget. It's called a solar pathfinder, and basically it is a curved reflective surface in which we can kind of see where things are going to hit. So you take your solar pathfinder out, you put it into the spot, you stand in the spot where you would ultimately like to have the solar panels, and then what you can see is the shadow, and it gives you a 365 view. And so it also shows you at the different time of year, based on where the sun is going to be, where those shadows are going to fall. And so we can take a look at this and we can say that, okay, well, right here, if this is where my solar panel is, this tree might cause a little bit of problem if we have the solar panels over here. There's going to be shading from our next door neighbor, so we don't want to put our solar panels there. And oh my goodness, this looks like a great spot because, as you can see, it's just sky. So this is a tool that we use when we go out to place the solar panels or determine whether or not a site is going to be good for solar panels, because solar panels are expensive. And if you are in a spot where there's not good solar access, then you have to think if it makes sense to put solar panels on the roof of that house, or if there's another way you could do it in which they're elevated more that would make them more efficient. Okay, so there's this other crazy thing called the angle of incidence. Anybody want to take a guess what that means? No, we actually use the angle of incidence for quite a few different things. And basically it means a ray is hitting something. A ray of something is hitting an object. So another example, if we're not talking about solar, for this would be flight. So wind or air pressure hitting an airplane wing. That's really important because you want that airplane wing to be at a certain angle so the airplane can lift, right, and fly. That's another instance where we'd be using this idea, this angle of incidence. So with solar panels, what we find is that when we have our solar panels perpendicular to the sun, we're going to have the most solar gain. So here we have, you can see the most solar gain. If I move over here, you'll see, okay, I've tilted my solar panel and I'm missing a few of those rays. And then over here, if you take a look, if it's really tilted, I'm going to be missing a lot of those rays. They're going to be hitting the solar panel. And so for the most efficient, you want it to be perpendicular. Well, of course, that's a little bit tricky because the sun is going to change throughout the year as to how high it is on the horizon. And also where it moves from north to south. So setting that up is going to be a little bit tricky. Now, there are ways that you can do it. They have, of course, invented something that will track the sun, and it moves the solar panel throughout the day and throughout the seasons to get the best angle of incidence. Otherwise, we have to calculate what is the most efficient angle for the majority of the year. And that's something that when we do, we have a chart that we look at, and it's very nice. They've calculated all of that based on what latitude we're at, and based on some other factors such as weather patterns for Montana. Okay, so one more thing to talk about really quickly here is the charts. And so, like I said, we have lots of other charts. So what this is also going to tell me is where I need to look. This is very similar to our solar pathfinder. It's going to tell us a little bit where the sun's going to be at what point in the year and at what spot at any given time. So you can see we have it a different time, and we also have a different angle of our sun. So this is very helpful. Again, we consult a lot of charts when we're doing this, a lot of different things. Okay, so I said I wanted to do a little math problem with you. Before we talk about the math program, I want to talk a little bit about, once again, energy and electricity. So watts, we just talked about those. Those are a measure of electricity. What two things make up a watt? Does anybody know?
Volts and amps.
Beautiful, volts and amps. So we have volts times amps equal watts. And when we're looking at that, we know that volts are, what do volts measure?
Quantity, I think.
So volts are actually going to measure electrical pressure. So how much pressure? How about amps? Anybody know what amps measure?
How much electricity is flowing?
The flow, exactly. So we have the pressure plus the flow gives us watts, and we can measure something based on that. We can't measure it we can't tell an overall energy output if we have just volts or just amps, but when we multiply the two together, we get watts, and we're able to get that. So, you guys do any of you have a little scrap piece of paper and a pencil that you can pull out? I have a little math problem for you. And if you have a calculator handy, you might want that. Okay, so, oh man, I like that it's great. You guys can just pull out your phones and use your calculators. That's super helpful. So, okay, so I'm actually going to move over here to a document camera just so I can do this problem with you. There's a lot of different math that we do when we are sizing a chart, when we are sizing a house for a solar array. But this one is just kind of fun because it gives you an idea based on the efficiency of the panels. Okay, so I'm going to just scooch over here to my document camera. All right, here it comes. There it is. There's my pencil. Okay, so we're going to be looking at a standard 80-watt solar array. So here's our panel right here. We've got the different little solar cells that are in it. The sun's beating down. We've got what are coming from the sun?
Photons.
Photons, exactly. And they're hitting what little things that are in here?
Silicon.
Our electrons, right? So they're making them move around. So they're doing the electron dance over here. They're boogieing, and they're producing some energy. Okay, so when you buy a solar panel, it's going to be rated. It's going to give you an example of what it's rated at. So a kind of a basic standard solar panel might be rated at 80 watts. And so we know that, okay, so we know we've got an 80-watt solar panel. And what we also know about this 80-watt solar panel is that it's broken down and it tells us, which is very lovely, what voltage in amps we've got. So this is going to be 17.1 volts, and it also has 4.68 amps. Okay. Now, we know that this is also rated at a certain degree. And so this is going to be at about 25. So our 80 watt, and they use Celsius because most of the world uses Celsius. 25 degrees Celsius is the average, is the temperature that we are looking at. Okay, so what we're going to do is we're going to take a look at this. 25 degrees Celsius, this is going to be our baseline temperature for this. So let's say that the temperature outside is negative 20 degrees Celsius. So we have negative 20 degrees Celsius. Now we know something. We know that voltage is going to vary. Voltage is going to vary 1/2 of every single degree. Or 1/2 of 1%. So that's a really tiny number. 1/2 of 1% of every degree Celsius change. So the delta T, so it looks something like this. Temperature change is delta T. So when we move that up, we got delta T equals 1/2 of 1% for degree change. Okay, so what does that look like? Well, we know that 1%, if we were to write it, is 0.01, and half of that is 0.005. So those are going to be some numbers that we're going to use. Okay, so first thing we have to do, if 25 is our baseline, we have to find what our delta T is. So we're using that 25 degrees as our standard. So if we have 25, what is the temperature change between 25 and negative 20?
40 degrees.
Come on, guys, that's easy.
Negative 45.
I heard it out there. So then we get, so our delta T, I'll get a new piece of paper. So our delta T is 45. Okay, so we have 45 degrees Celsius. Okay, so then what we have to do is we have to say, okay, well, for 45 degrees delta T, how many degrees of change we have, it's going to change 1/2 of every 1%. So that number that we used was 0.005. 0.005 times 45 is what? Anybody want to tell me?
I got it.
0.225.
Yeah, 0.225. If you take 0.225 and you change that into a percent, what percentage do you get?
22.5.
Yeah, or 22.5%. Okay, so then when you take the number, they would take 2.225, and because we are talking about volts, we're gonna multiply this by 17.1 because that is what our voltage is for this particular solar panel, and the number we get is, who wants to tell me?
3.848.
Okay, so 3.848, so we're going to call it 3.85 just for fun. So we have 3.85, and that is volts. So we have a difference of a 3.85 increase. So then what we're going to do is we'll take our 3.85, and we're going to add it to the 17.1, which is going to give us 20.95 volts. And this is our new fancy number, 20.95 volts. So then we put that into our original volts times amps equal watts. So we now have 20.95 multiplied by that original number, which was 4.68 amps. That's going to give us, anybody want to tell me?
98.1.
98.1. So this was a solar panel that was producing 80 watts. So at any given time, this solar panel at 25 degrees Celsius could produce 80 watts. If we brought the temperature down to negative 20 degrees Celsius, suddenly the efficiency of that panel went up to producing 98.1 watts. How many old-fashioned light bulbs could you run on that?
1.
At the coldest temperature, you could just barely move. You could just barely run one light bulb. So you can start to see how needing lots of solar panels could add up very, very quickly. Now, I'm not going to make you do it right now, but I do challenge you. Let's say that it was the opposite, and it was 45 degrees Celsius instead of negative 20 degrees Celsius, which is about 113 degree temperature. So a really, really hot summer day in Montana. I challenge you in a little bit after the video conference to work that out and see what the efficiency of the solar panel is if you were to use that number. And you'll find what ultimately you're going to find is that our efficiency goes down. So those hotter days in the summer, even though you might have more sunshine, the efficiency of those solar panels is going to go down. So that's all very, very important. Like I said, when we're sizing a system, we're trying to figure out what, kind of what works. Pull these pictures back up. Taking a second, thinking about it. There it is.
Hey,
Okay.
Allie,
Yes.
I have a question.
Yes.
To make sure I understood. So the colder it is, the more efficient the solar panels are?
Correct. Yep. The hotter
All right.
it is, the less efficient. So use that same problem, and put in the higher temperature, and you'll find that the efficiency goes down quite a bit. So when we're looking at solar panels and when we're trying to figure out how many solar panels we need, we have to take into account those average temperatures. Okay. So recently, one of the schools.
Allie,
Yes.
grab her. We have a 4.7 kilowatt hours system at Helena High. Can you quantify that for us?
Okay, so
How
4
much
point.
energy?
Okay, so that's a great question. Okay, so if you have 4.7 kilowatts, how many watts do you have?
4,700. 4,700.
Okay, so we have 4,700. And actually, I'm going to go right here to this thing, and we're going to pop on to a little chart, which is kind of fun. And I can send you the link to this. It's going to take a second to load. So one of the things that we do when we are sizing a system is we can use things like this load chart. So if we take a look at this, what we do is we can put in information as to typical wattage. And so what I'm looking at right here is what you would do is you would find out what each of these things use. Now this is more set for a home as opposed to a school. In a school you're going to have different loads. When I talk about loads, a load is how much something takes from the electricity. So a load of a computer, how much electricity does it take to run that computer? Or how much electricity does it take to cool the school or heat the school, depending on which you're doing. So those are all what we refer to as loads. So if we take a look at this, we have this in watts. So a microwave is going to typically, when you use about 1,000 watts or 1 kilowatt. A dishwasher about 1,200. A toaster about 1 kilowatt. So these are all different things that we're going to be taking a look at. So if you have 4,700 kilowatts, right, that you are using or that you have access to, you can start looking at the different things. You can maybe count how many computers do you have in the school. Are they all running at once? Are they all using? Is there a different way that they're using? Is there a way that you can have them in a power saving mode? Do they have a sleep mode? Can you turn them computers off when they're not using? All of those things are things to think about as you are thinking about that. So if we go down here just a little farther, it's going to tell us.
Hey, Allie, I'm going to interrupt. Allie.
Yeah, go ahead.
2 years ago, we got a directive from our head computer guy, who's no longer here, to never shut off our computers.
Oh, yeah, that's
and they were
tough.
on for a big part of the summer. They're on for vacations, nighttime, everything else.
I don't
And we
recommend
tried
that.
building. Can you believe that?
No, I can't. I think that's absolutely ridiculous. Because if we take a look at this, what computers are actually using quite a bit of energy, and I'm taking a look at this right behind me, so we find where our computer is. So 30 watts, desktop computer, 100 watts, a laser printer, a kilowatt. So all of this is going. And then the thing that's crazy is that those are kind of low numbers, but then when you start thinking about how much they're actually using over the course of the day, or what you're asking them to do, because certainly, have you ever found that if you take a laptop, or let's say your phone, I think this is a really great example. If we take our phone, and you have different apps on your phone, right? Have you ever found that some apps use more energy than others? Yeah?
Yeah.
I found that to be true.
You want to stay here? let me know and I can try to explain it. You can grab a whiteboard right there. Trust me, bring it up. Tell her that half of us will stay. Kira, you can tell her that half of us are staying.
Yeah, half of us are staying.
Okay, sounds good. Okay, so so let's say you have your computer or you have your cell phone and you have an app. I noticed that Facebook app on my cell phone takes up a tremendous amount of energy. Has anybody found that to be true?
Right?
Yeah, like if you run that app on your phone, your battery goes dead really, really quickly. Well, it's the same with a computer. So these are general standard things. When we're running our computers, when we're doing different things with our computers, they're going to be drawing more electricity. They're going to be drawing more energy. And so these are, like I said, these are very basic numbers, but you can think about that. Even when your computer is not doing anything, when it's in sleep mode, it has what we call ghost loads. Ghost loads are when things that don't really look like they're doing anything, but they do. That little blinking light that's on your computer, it takes energy for that little blinking light to continue to blink. And so that's kind of one of those phantom or ghost loads that we see. And after a while, if every teacher in the school has a computer that's on and everybody's light is blinking 24 hours a day, 103 or 365 days a year, suddenly that's a lot of energy that you're using. Now from a computer standpoint, there's lots of ways that you can do this. You can put your computer in sleep mode, which is going to reduce that. It's not going to fully take it away. One of the things that we recommend people doing is having a lot of their appliances or their things that might be on, that have ghost loads, on a power strip, and being able to turn that off so that you can completely shut everything down. Ultimately, that's going to help. So we think about, and I have to go ahead and look, and one of the ways you can look is you can go ahead and get records from how much energy your school uses, because you are a school, it's a place of business, it has to pay an energy bill, and the energy company has to keep track of how much energy your school is using. And so one of the things that you could do, a very easy way, is to find a copy of an energy bill for Helena High School. Helena High School could take a look at it. You could see on average how much energy you're consuming over the course of a month. Now, it's not going to break it down into a course of a day. It's more general. You'll have to look at things a little bit more closely. You could also go ahead and take a look at individual things. You could look at the back of the computers, and a lot of times they'll give you an energy output on those things. Another thing that's really fun is a little device. I don't have mine here, but they're called kilowatts. Your school might even have a kilowatt. Does Helena High School have one?
I don't know.
Probably.
They're really funny, and actually it's something that would be really neat to have to play around with, just to get an understanding for how much energy things use. And it's a little teeny tiny box, and you plug it, basically what you do is you plug it into the wall, and then you plug whatever you want to measure into the kilowatt, and so it'll just tell you how much energy is going through the box, so how much energy whatever you have plugged into it is using. And you can try doing different things. You can plug in, if you have the right adapter, you can plug your phone in, and then you can turn on the Facebook app, and you can see exactly how much energy that is zapping. Or you could turn your computer on, and you could try different things. You could put it in the sleep mode. You could have it up and running, and you could check, and you could see how much and how that energy fluctuates, because it's in real time, and it'll give you a number in watts or in kilowatts that'll tell you how much energy it's using. So that's a really good way to do it. You could get one of those. You could go around to each of the computers in the school, or to a computer in the school, check them, and then count the amount of computers you have to get a rough estimate of how much energy your school is using as a whole. Energy levels vary considerably between houses, between businesses, based on how people choose to conserve energy, or what measures they have in place, or even what appliances they have. A house that doesn't have a TV is going to probably use less energy, because televisions use quite a bit of energy. But there's a lot of difference, and people always ask me, well, what's the average amount of energy usage for a home in the United States of America? And I like to tell them that there really isn't an average. There are numbers that you could say, okay, an average house uses this amount, but there's so many different factors that go into it. It's almost like comparing apples and oranges. You have to account for the amount of people that are in a house. You have to account for the activities they do, what time they're at the house, when they're at the house, if they're working, if they're not working. All of that is going to play into energy consumption. Okay, so I'm going to go back here. I'm going to pop out of this. If you go to...
Alex?
Yes.
Allie?
Yeah.
So I missed part of that, but so if you, the more programs you have running, the more energy you're using?
In certain situations, and I was likening that to a phone, and that's one of the things that you really find is that when it's a great example is that if you're a lot of the applications that you run on your phone are going to take more energy than others, and so if I run certain applications on my phone, it's going to use a lot more energy. Another example, your toaster. Let's say you like your toast, I don't know, on a number 2 setting, and then your brother likes his toast on a number 7 setting. What's going to take more energy?
7.
Probably the number 7 setting, because it's trying to make that toast a little bit darker. And so there's a lot of different ways that when we use when we're using energy and when we're using appliances, that we can alter things or that they use more. Did you know that a freezer is going to be the most efficient when it's full? Crazy, right? Interesting. So there's different ways, and that's why I said if and I was telling him about a kilowatt, and I was wondering if Helena has a kilowatt or if you've ever used a kilowatt.
Yes, we used to have an environmental studies class until not enough kids signed up. And so now we don't. So this is the club, this volunteer club right here. And when we had the class, we went around and stuck those little meters in and measured some things. I'm an English teacher, but that was a science teacher that was organizing all that.
Yeah, and so those are really, they were saying, well, they asked like, well, how do you know what you're using? And that's a really fun way to do it. It's very easy. You just plug it into the wall and then plug whatever you're testing into the kilowatt. And the kilowatt will read in real time. And then you can play around with things too. Like you can run a different app on your phone, or you could turn the toaster up to a 7 as opposed to a 2 and see the differences. And those will all give you an idea of how much energy you're using and what those consumption levels are. So one of the first things that we always say to anybody when they're considering solar is we say, well, how can you conserve energy first? And what types of things can you do to conserve energy? Because if you're conserving energy, you're going to be doing a couple things. One, you're using less of it, so you're going to need less, which equates to less solar panels, which means a lot less money. And it's a very easy thing to say, well, if you use less energy, it's a lot less money. Also, if you're grid tied, that means you're still using electricity that might come from the grid at different times of the day, say at night when your solar panels aren't producing any energy. It'll be a lot more efficient, a lot less of a cost to run things. So we always say, let's look at our efficiency. I talk about Hawaii a lot, and the reason I do that is that they're quite progressive with the idea of using solar energy in many different ways, but then also in conservation units. And so the energy company actually sponsored a really big program, and it was to trade in old refrigerators, because one of the most inefficient things in your entire house for a long time was the refrigerator. And so they gave kids little magnets to take home that had pictures of refrigerators that were like, avocado green and teal and pink, and they said, if you have a refrigerator like this, bring it in and we'll give you $200. And so what they did is the energy company collected all of those older refrigerators and gave the families $200 to go out towards a new, more energy efficient refrigerator. And it can cut down quite a bit energy saving measures that are simple but also larger, like replacing appliances, can cut down the overall consumption of a household by over a third to even a half, depending on the measures that you take. So when we're looking at things like solar energy, there's a lot of it, but it's also expensive. It's not for free unless it's passive. And if we're going to be paying for it, we want to make sure that we get the best bang for our buck. So conservation methods, changing your light bulbs, making sure that you don't have any leaky doors or windows that are going to have the air come through. Those are all conservation methods that are going to lower how much energy your total consumption that your house needs to use. Okay, so if you guys want to, you guys can go take a look, solarplexus.com. And then you can if you type in load chart after that, if you Google load chart, it'll bring this up. And what it'll do is you can put in your you can put in your the loads that you find, and it's kind of a fun tool. You can use this. You can even use this for the school. A lot of this stuff will be there, and when you do that, you'll get a good idea of how much energy you're using all together. You can also make your own charts or use it as a guide based on what's applicable and what's not. And that'll give you an idea. It'll also give you an idea of what your solar panels are using and how much they're taking account, like how much they're using for the school or how much they're helping the school, which is a pretty interesting spot. Okay, so I'm going to pop out of this really quickly, and I'm just going to show you some pictures of a solar installation that we do. So let's say it's time to install. This is a solar installation, excuse me, recently from a high school in Missoula. And they actually had a group of students that was in a special class that was developed just for the purpose, help install. They learned about solar production, they learned about how to install things. They went through an OSHA safety training class, a lot of other things. They had to learn some of the electrical and mechanical components to putting in solar panels, and so it was a semester-long class, and one of the culminating events was actually helping Solar Plexus install these solar panels on their roof. So what ultimately they ended up doing is we have to lay everything out. You lay everything out, get everything right, you get the bracing for it, and you have your design. You figured out how many solar panels you're going to need, and sometimes that depends on how much money you have to spend on solar panels. Other times it depends on how much energy you want to try to, how much energy you want to try to have the sun produce for you. So there's kind of those two factors that are going to go into it. As a lot of these pictures are just the kids working alongside of the people over at Solar Plexus to get things set up. So we have the bracing inside of the bracing set up. We've got to make sure that everything is just so. As we learn when we're looking at angle of incidence, as we're looking at what season it's in, if we have things that are kind of sloppy or messy or we don't do it the right way, it's going to reduce the amount of solar energy that those solar panels are going to produce. And that's ultimately the goal, is to try to make the most energy with the materials that we get. So it's a pretty tedious project. Go through it. This took about a week to complete the install on this. They had quite a few arrays. I think they had, goodness, I'll have to double check to see how many panels they ended up with. But it was a good size array. I don't think it was quite the same. I don't think it was quite as large as the one that Helena has. And like I said, part of that depends on how much money is available and how much funding is available, and also what they're trying to offset. So we have the bracing, we have the brackets. As we go along, these are eventually going to help with where the panels are placed, how they're going to be tilted, what degree they're going to be tilted at, working on installing. You can see that once you have everything laid out, it's really a grid-like form. We're getting close to actually putting the panels in. We have these blocks. These blocks are going to help weight down the panels, make sure they're not going to go anywhere, because certainly brackets are strong, and we want them to be strong, but top of a roof can be a pretty inclement place. Then we have to have the electricity. I want to make sure that our panels are grounded. That's super important, obviously. We don't want any mini electrical storms happening up there on the roof. So they're grounding the wires, they're running the electricity through the conduit. The conduit is going to go down into the inverter on the side of the school, where that direct current is going to be changed into an alternating current that can be easily used in the school. Lots of wires, lots of wires for it. And then they're getting ready to set the panels, which is really exciting. And you can see them right here. See the mounting brackets that they have. So they have the mounting brackets. They're at about a 45-degree angle to the sun. They're setting them in place. And here we go. We have our array. It's ready to go. It's up and working, and it's going right now. So I want to share with you, and I want to also hear questions that you guys have as well. But one of the things I want to show you is I actually have solar panels on the roof of my building right now. And I want to take a look. What I do is I also monitor mine. And so we're just going to go to this website right here. It's going to take a second to load. But this is a monitoring system. And so I have a monitoring system set up with my solar panels, so I can actually see what is being produced at any given moment. All right, so here we go. These are the solar panels that are on the roof of my shop today. Anybody want to guess what the weather is like in Missoula right now? Or was like recently?
It was warmish, but kind of still kind of cold.
Is green more efficient and red less efficient?
Okay, yeah, so the first thing you gotta do is figure out how to read this. And so this is a 1 day view. Let's go to, I'm gonna go to the 1 week view. It's gonna give us a little better picture of things. Okay, so let's take a look at this. So the green is the energy that's being produced by the solar panels, okay?
Very educational. Pay attention. She's just about that. Oh, thanks. Okay, thanks.
The red right here, this is my load. This is the energy that I am using. And because I'm in a place that has a lot of computers and things that aren't turned off, like servers, which you can turn off computers, but generally you don't turn off the server in the server room because you just don't. Those are things that are going to take a lot more energy. And so I have a pretty consistent load. In fact, if we look over here, I have consistently about a 1 kilowatt load. Now, I also have something, a little spike. What do you think spikes? It spikes like almost every, 15 minutes. What do you think that could be?
The sun rays, like going up and down, because the clouds obviously cover the sun. And then
It could, but it's so consistent. I know that what this is, the little red thing, is that's actually an internal load. So that's something that's happening, and it could be one of a couple of things. It could be something like the server recycling, an energy storage. It could be we have a little refrigerator in here. It could be my refrigerator turning on to cool down. As a refrigerator, it'll cycle, and so just like many appliances, it'll cycle on and turn on for a few minutes and then kind of go into more of a power saving mode. And so those could be those little blips. But you see that when you're looking at this, and this is fun, this is when you get to be kind of the detective. And we've actually just discovered some really fun things by looking at this. Found things that were on or that were working in a way that they should not be working. And the way we discovered it was because we saw really high spikes in our energy, or we also found really low things. And when you look at that, you go, uh-oh, something's wrong. Something's not supposed to be, it's not going appropriately. So another thing that's kind of fun that you can see is there was something happening over the weekend here in the studio, and I don't know what it was, but there was definitely more energy consumed over the weekend, not when I was in here, than our normal energy consumption. Okay, so if this is our normal energy consumption, and then this is what our solar panels are producing, and you can see, so Thursday, we might have had some sunshine. It's possible that we actually had some sunshine, and that for sort of that a few hours during the day, we were producing more energy than we were consuming. Friday, what do you think? Cloudy, sunny?
Cloudy.
Cloudy.
Pretty cloudy, right? Saturday, a little bit of both, maybe. And Sunday, so it kind of goes on. You can kind of take a look at it. Right now, you can see right here that we're actually producing. Ooh, it's going up and down. Now it's really down. So what do you think is? Okay, this is sort of fun. Looking at this, what do you think the weather is doing right about now? What do you think we have? What kind of cloud cover or not cloud cover do we have?
Scattered. Changing probably.
Yeah, I think it's scattered because it's almost up to 2 kilowatts. But a second ago, it was down to it was below, way below 1. We were into the watt zone at that point. And so I bet it's funny. I'm in a big building that doesn't have a lot of windows, and especially the room that I'm in right now has no windows. But I bet if I were to go outside, I would see predominantly cloudy sky with a few little sun breaks in the clouds. And so you can really kind of see oh, look at that. Here we go. So it's sunny all of a sudden. I bet it's sunny right this very second in Missoula, which is great because in the winter it doesn't get to be sunny that much. So it's a fun way, and it's a neat way to sort of go ahead and see how much energy you are producing, how much energy you're using, and then what you can monitor too is you can also monitor your conservation efforts. And you could see all the teachers are supposed to leave every single computer on 24 hours a day, 365 days a year. Well, we now have a baseline for how much energy that is. Well, what if we turn them off at night? We could go back and we could look and we could find out really what that looks like over, we could compare it. We can go back really far on this one. Let's go back 6 months and let's see what the difference is 6 months ago. Okay. Um, so September, still pretty sunny. As you can see that we were actually making quite a bit, most of our energy. We really had very, very little energy demand. You can see that come October, the sun's sort of starting to wane. November, December, January, relatively dark. And we're using quite a bit of electricity too. So you can see the difference, the seasonal changes. If I go back a year, that'll give us quite an advantage. I just gotta think about this. I'm gonna scooch off so you can see it a little bit better. But you can really see how seasonally the amount of sunshine affects those solar panels. We also have a little bit of shading where we are. We have a hill that is pretty close to us, and so in the wintertime, there's parts of the day where the sun doesn't make it over the hill until later. We're actually in kind of a canyon where I'm at right now, and so you can see all that. So this is important, and these are all tools to help us efficiently use solar panels, and also to think about energy consumption and also energy conservation, what we're using, what we can do to conserve, and how we can use the sun to help produce energy. So do you guys have any questions before we go today? I know it's a lot of information I've given you, a ton of information.
Branson, go ahead.
So I had a question on how much you know about excess electricity, or what is called dirty electricity, that is produced from other appliances and household things, you know.
So I don't know a lot about that, and so let me see if I understand correctly. So what you're saying is that is it energy that is being used by those appliances or actually produced?
Yeah.
Produced?
Used.
Used.
So,
Okay.
yeah.
So energy that is used, and that's kind of when I was talking about the ghost and the phantom loads, is that anytime you have something plugged in that's an appliance, chances are very, very likely that it will be using energy during the time that it's plugged in or it's on. And so, and those are kind of what we refer to as those ghosts or those phantom loads. And so that's one of the things where if you have appliances, now you obviously don't want to be turning your refrigerator off in the middle of the night. You'd have a lot of melted ice cream. That wouldn't work. There's some things that you just have to keep on, have to keep going. But there are things like your computers that in the middle of the night, you probably don't need on. I know a lot of us have our computers set to do updates in the middle of the night and so we have to leave our computers on so that they can update in the middle of the night. Well, you can work around that. You can say, okay, I'm going to update. I'm going to take a time where my computer is going to come on at a certain time. And when it comes on, you can program that. You can program those to come on. Or you can also turn them on, set it aside, and program the computer to say, okay, you're going to do your update during this time of the day. I know that I'm typically not using my computer. It's going to happen once a week, and it'll do it. Or once a week, I'm going to leave my computer on overnight, but not every single night. And so by doing those and using power strips where you can turn off all energy that goes to those appliances, you're going to prevent that from happening. You're going to sort of prevent those phantom loads. Now, another thing which kind of made me think of is what happens when you're tied to the grid, so you're still using grid electricity. When you have your solar panel, you're producing energy during the day, you're not using a generator, you have it tied to your house through an inverter, and you're also part of the grid. So at nighttime, when your solar panels aren't working and you want to watch a television show, you can still do that. Sometimes what ends up happening is that we produce more energy than we need and more energy than we use. And there are ways that you can then sell that energy back to the power company and put that back into the grid. Now, one interesting thing, I was talking recently to a professor at the university, Dr. Steve Running, and he's pretty phenomenal guy. He actually won the Nobel Peace Prize, was a recipient, and he does a lot of work with energy. Okay, and this is his thing. And so he said, the future of energy, I believe, is not going to be a ton of big power plants, brand new power plants all over the place, or a huge area the size of South Dakota, that's all solar panels, that's going to provide all the energy for the United States. He says, I think the future of energy is going to be everybody's house is their own little power plant. And we're going to get smart enough so that when we build houses and our technology is going to develop so that we build our houses and we use this technology we put solar panels on our house, that our houses are all going to be producing more energy than we can use. And because they're producing more energy than they can use, that energy is going to go and it's going to feed into other things that require more energy. I think that's the energy of the future of energy. That was one of his comments to me. I thought that was a very, very interesting way to think about the energy future and kind of how we're moving through this and how each of us, no matter how small a part we can play, it really does matter and it really can make a difference and an impact. So does that answer your question at all?
Yeah, very much.
Good. Do you guys have any other questions? Or comments or thoughts? It doesn't just have to be on solar too.
I've got a question. I'll sit over
Yes.
here. Hi. Okay, we have a 4.7 kilowatt hour solar panel we installed a year ago in July.
Uh-huh.
We also have something here. We're going to design a kiosk to display the energy information, much like you have right here, so that students can
Very
see it in the
cool.
hall as they walk by. But for some reason, we got like the old-fashioned version, which only has like a once weekly list of
spreadsheet.
just a spreadsheet.
Yeah. Just a spreadsheet.
It's very
Okay.
boring, very boring to look at. Nobody can interpret it. We totally need help down here. Do you want to come down to Helena High? Help us figure out. We could probably pay you something. Help us figure out how to make this kiosk interesting. It needs to be like this. The science and the math departments to actually use the data in their classes. That was the original part. We got
Very
2 grants
cool.
for that. One from Northwestern Energy, one from Helena Education Foundation. And we just kind of got stuck here until my friend Bill Kaiser came to try to help me. And we need some more help.
You know what I
that'd
would
be
say?
my
Let's send me if you send me one of those. Send me one of the data sheets or send me a link
Sheet?
to it so I can take a look. Let me look at it. What I'll also do is I'll also ask my buddies over at Solar Plexus. I also work with another individual, Ryan, who does a lot of stuff. This is a company called eGauge that I've worked with a lot, and they're a great energy monitoring company. There's a bunch of different energy monitoring companies, but they might be able to help you translate that data. And I'll take a look at it too and see if we can look at that and say,
Yeah,
okay.
We need help. It's Fronius. We not only do we have energy stuff, we got temperature monitors, we got wind speed monitors, and we're going to take all this stuff and offer it to the science classes. But then,
But what do we do with it?
Help us.
Definitely. I'd love to help you. I love projects like
We need
that.
help.
I love projects like that. That's really exciting. My favorite part of energy is the detective work that goes into it, and is looking at things, looking at data, looking at the big picture and saying, okay, I know this little piece of the puzzle, I know that little piece of the puzzle, I understand what's happening here, but what does it mean when you put it all together? And what do those numbers show us about ways that we can conserve energy or ways that we can use alternative energy to offset those energy costs? And so that's, in my mind, that's super exciting work.
So Allie, I'm excited like you. I gotta tell you, back here as my English class, they're waiting to do English, so I probably better say goodbye. But right here is our green group class, and I'd really like you to know that these kids right up here and some other ones that aren't here today raised a lot of money because our grants didn't cover the entire cost.
Awesome.
So a lot of concessions. Work their butts out. They recycle. They're working on educational things. They're trying to make a difference. And so I just want you to.
That is awesome. Well, you guys, that is so great because you know what? We need the people like you. You are the future, and there's a lot of energy stuff that's happening in this world right now, and there's a lot of waste that's happening in this world, and it's going to be your generation, and it's going to be kiddos like you that figure out the solution and that work with each other and work with other people to let them know what's happening and to find those solutions. So I'm always so encouraged when I meet students like you that are working towards a goal like that. And I would be happy to help you in whatever capacity I can to get your kiosk up and running and to make it interesting and applicable. All right, you guys. Hey, thanks so much. Have a wonderful day.
Thank you.
Thank
This
you.
You
was
bet.
great.
Bye,